Hey, honors chemistry. It's Tuesday, April 7th. I think we're going to have one more day after this on this chapter 16. But I want to go ahead and make some, in a practical way, some heads and tails out of this thing. Common sense. Take a look on page 519. You're going to see an equation right in the middle of that page that looks like this. So you got ethylene with hydrogen forming ethane. And so what we have here is we got 2 moles of gases going in and 1 mole coming out. So what are you going to tell me about delta S? Positive or negative? If it's going from more randomness to less randomness. Negative. And what do you get when you have a delta H negative and a delta S negative? Well, it could go either way. And at lower temperatures, let's go ahead and put that formula up there again. Gibbs free energy equation. Okay, so at low temperatures, and delta S is negative, a negative times a negative is a positive, and that's not going to influence it very much. That's not going to influence. This thing here is a negative, and this is a positive, but it's a little positive. And so the negative delta H enthalpy predominates. And so as a result, this thing is going to be spontaneous. Now let's take a look at the next equation. You see that we've got 1 mole and 1 mole of gases. That's wild and crazy. A lot of high entropy, a lot of randomness. But then it becomes 1 mole plus 3 moles. It becomes 4 moles of randomness because these are gaseous products. So 2 moles becomes 3 moles. It becomes more random. So delta S is going to be positive. Now, delta H is positive when you have to put heat in. It's endothermic. And delta S is positive when it becomes more random. And so this is working against spontaneous driving it towards the right at room temperature. And this is working toward driving toward greater randomness. And which one wins? Well, when you got 2 positives, you can look on the table down there. It depends. If it's at higher temperatures, then this one will become spontaneous. Because if you have high temperature, that T delta S term will be big. And if you have a big positive term here, and this over here is a positive, the negative times a positive is a negative, big negative, it's going to predominate over the positive enthalpy. So at big temperatures, this will be spontaneous. And at small temperatures, it won't. That's what they're trying to discuss on page 519. Okay, I'm going to give you a few more equations, and I want us to discuss this. Tomorrow, we'll do the math. We just plug and chug into that Gibbs free energy equation. It should be pretty easy. All right, let's take HCl liquid becoming HCl gas. Hydrogen chloride is vaporizing. It's going from liquid to a gas. It's going toward more randomness since it's becoming a gas. That's called a change of state. And if it goes toward more randomness towards the right, that makes delta S positive. But coming back to the left, delta S would be negative. So the randomness would go up if it goes to the right. Randomness would diminish if it comes back to the left if it condenses. It's vaporizing going that way. It is condensing. If it's going this way, it's a two-way equation. We call those equilibrium equations. So answer this question. State whether the change in entropy, delta S, favors the forward or the reverse reaction. Well, doesn't it drive toward disorder? So it favors going forward. Get the idea? All right, let me give you another one. These are on your worksheet, by the way. We got C6H12O6. Any idea what that is? Glucose. Yeah, simplest form of sugar. And it's in the aqueous state, so it's dissolved in water. And then it becomes C6H12O6 solid. Which one is favored? The forward or the reverse equation? Forward meaning to the right, reverse meaning to the left, for the change in entropy. Well, let's see. If it goes back to solid sugar crystalline, let's just say this. Right here, it's dissolving. And right there, it's recrystallizing. In other words, it's coming out of solution. And so if it's recrystallizing, it is becoming more defined and less random. So delta S is going to become negative. This dissolving thing, delta S, is positive because it becomes more random. So which is favored? Well, it favors going toward more randomness. So it would be the reverse reaction in this change of state. Now let's take ammonia, NH3, and turn it into its constituent elements. Nitrogen and hydrogen. So the ammonia, all three are gases. Okay, now we got to balance this thing. 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. So do we see 2 moles of gases over here? And do we see 1 plus 3, which is 4 moles of gases over there? That is going toward greater entropy in that way. All that positive. Okay, don't forget when delta H is positive, it works against spontaneity. When delta S is positive, it works towards spontaneity. So the forward reaction is favored in this case. Let's go C2H4 becoming C6H12. And C2H4 is gas, and C6H12 is a liquid. Didn't they forget a reactant here? That seems odd. Well, I don't really like that. Anyway, the more random would be to the reverse direction because it's got the gases. Okay? You know what the expression is for enthalpy? We'll be using it again tomorrow. Delta G equals delta H minus T delta S. And the sign has to be negative for spontaneity to occur at room temperature. Okay. Now, let's consider this following equation. Ammonia plus liquid water and it's in equilibrium, so it's a two-way equation. NH4 aqueous. So you're adding ammonia to water, you're getting ammonium and hydroxide ions and energy. So if energy is being released, let's ignore that part of it. If energy is being released, delta H is negative, right? Exothermic. Going in that direction. But if you're trying to drive in this direction, energy becomes a reactant, and so it becomes endothermic. Going, whoops, going this way. Exo, going forward, endo, going in reverse. What I'd like to know is, does the enthalpy factor favor the forward direction, forward reaction, or the reverse reaction? The enthalpy is negative, it favors going forward. Most chemical reactions in nature are exothermic, releasing heat. And now, what about the sign T delta S? Is it negative? If it's negative, that means it's becoming more ordered. This means that the entropy factor favors heading backward in the reverse direction. This favors going forward, and this favors going backward. Okay. Now, at room temperature we're talking about. So if the temperature were higher, then it's still going to be negative. So I'd talk to you about that. All right, how about this one? One more to go over. Water liquid is becoming water gas. And equilibrium is set up. You can see that with two-way arrows. Delta H is positive 40.65. Positive 40.65 kilojoules per mole. This is at a high temperature, at 100 degrees Celsius. You got to get that liquid up to boiling point before it's going to turn into a vapor, the vapor of water. Now, is the forward reaction exothermic or endothermic? The forward reaction. You're correct. Endothermic. You got to add heat in order to get it to vaporize. Does the enthalpy factor favor the forward or the reverse reaction? Well, enthalpy favors going negative. And so from the viewpoint of enthalpy, it would like to be going that way. Because delta H should be negative going that way. It would release heat. When you condense something, you release the heat of vaporization. Remember the molar heat of vaporization that we talked about earlier, previous chapter? Does the entropy factor favor forward or reverse? Entropy. Well, that favors going in reverse because entropy is going to gas. And that would be positive, becoming more disorderly. That's all I'm going to talk to you about. Tomorrow we'll do the math. See ya. Be good.